everyone, welcome to another class of CPA101 Fundamentals of Electrical Circuits. So today we're going to discuss about capacitors and inductors, but before that, let me share to you this quotation for today. And so once you replace negative thoughts with positive ones, you'll start having positive results. So just like the law of attraction, if you keep on thinking positive things, then of course you'll attract all the positivities. And if you keep on thinking what ifs, all worries, negative thoughts, and of course you won't be able to see the positive things in the middle of those problems that you're encountering. Okay, so whatever you expect with confidence will be your own self-fulfilling prophecy. So by the end of this module, our learning outcomes, you should be able to first familiarize with capacitors and inductors, apply circuit theorems in solving circuits involving capacitors and inductors, and understand the application of capacitors and inductors. Now let's start with capacitors. So what is capacitors? It is a positive element designed to store energy in its electric field. So besides resistors, capacitors are the most common electrical components. It is used extensively in electronics, communications, computers, and power systems. So physically, consists of two conducting plates separated by an insulator, or what we call as the dielectric. So as you can see in this figure, we have here two conducting plates, and this is a metal plates, each with area A, and a dielectric with permittivity epsilon, and a distance d, the separation of the two conducting plates. Now here is the capacitor with applied voltage. This is the representation of that, and for this third figure, we have here the actual pictures of the capacitors. So we have here circuit symbols for capacitors. So this one is for the fixed capacitor. So whatever the value of that capacitor, so it will not be changed. Then this one is for the variable capacitor. Okay, and we have here also some figures or image for the fixed capacitors: polyester, ceramic, and electrolytic. So this is the most common type of capacitor, this electrolytic, which has polarity, positive and negative. Then we also have here variable capacitors. So those those capacitors that can be adjusted. Okay, so the capacitance that can be adjusted. So examples of that are a trimmer capacitor and film trim capacitor. So these type of capacitors are used in communications, like in creating or constructing a transmitter receiver. Okay, so those are some application of these variable capacitors. Now we have here some markings of capacitor. Consider a 6.3 volts 1500 microfarad capacitor. So the maximum voltage across the capacitor should not exceed 6.3 volts. Otherwise, a leakage or breakdown may occur. And the second one, the capacitance value, the 1500 microfarad, means the capacitor holds 1500 microcoulomb of charge for every 1 volt of voltage across it. So for every electrolytic capacitor, so you're going to see this kind of markings. So the voltage or the maximum voltage and the capacitance it can hold. Now we have here a term capacitance. It is the ratio of the charge on one plate of a capacitor to the voltage difference between the two plates measured in farad. So we have a formula Q is equal to CV, where Q is the charge and C is the constant of proportionality known as the capacitance of the capacitor. The unit of the capacitance is the farad in honor of the English physicist Michael Faraday. So 1 farad is equal to 1 coulomb per volt. Now, if you will consider an isolated conducting sphere, we'll have these formulas. So C is equal to Q over V and also equal to 4 pi EA, where E is the permittivity and A is the radius of the conducting sphere. Note that the Earth's capacitance is large compared with that of other conductors used in electrostatics. Consequently, when a charged conductor is Earth, it loses most of its charge to the Earth or discharge. And so we have V is equal to 1 over 4 pi E times Q over A. And this permittivity is actual in our calculator if you have 570 ES or 991 ES. So E is the constant number 32. Okay, so this one. So you can see it in your calculator, that is constant number 32. So let us apply this formula in this example. So find the maximum charge stored by the capacitor shown in the figure. So let's have the formula Q is equal to C multiplied by V. Our capacitance given is, of course, this one written in the marking, that is 1500 microfarad, and the maximum voltage, which is the 6.3 volts. And let's put it in our calculator. That's 1500 micro. Micro is times 10 raised to negative 6, then times 6.3, and we'll have 9.45 millicoulomb. Okay, so charge, unit of charge is coulomb, unit of capacitance, farad, and unit of voltage is volt. So always remember the units of these parameters. Okay, now let's have another example. Find the capacitance of the earth given that the radius of the earth is equal to 6 times 10 raised to 6 meter. So let's use the formula that we have earlier. So C is equal to 4 pi EA, where E is the permittivity of the material and A is the radius. Okay, so 4 pi times constant 32. So I'll just write it as constant 32, or 8.854 times 10 raised to negative 12, and A is the given radius, which is 6 times 10 raised to 6 meter. So our answer would be 667.59 microfarad. Now, in terms of its physical characteristic, we can solve for the capacitance. C is equal to EA over D, where E here is equal to EO. EO is the constant 32. Okay, so that's 8.854 times 10 raised to negative 12, while the E sub R is the relative permittivity of a material. Permittivity, ayan. So in this formula, so A is the surface area of each plate, D is the distance between the plates, and E is the permittivity of the dielectric material. So in general, we have three factors that determine the value of the capacitance. So as you can see, our capacitance is directly proportional with our surface area, which means the larger the area, the greater the capacitance. And the spacing between the plates, which is the D, so the smaller the spacing, the greater also the capacitance, since they are inversely proportional. And lastly, the permittivity of the material. So the higher the permittivity, the greater the capacitance too. Okay, so that is the capacitance when considering the physical characteristic of our capacitors. Now, here are some relative permittivity depending on the material. So common is air, equal to 1 Then dry masonry, moist masonry. We have water. So this is 8 to 1 relative permittivity. Now let's apply the formula in this example. So calculate the capacitance between two parallel plates, each of which is 100 centimeters squared and 2 millimeter apart in air. So C is equal to, let's write it as EOER. Let's make this as capital A because this is area. Then over D. So our EO is constant 32. Then ER, our relative permittivity for air is equal to 1. So I'll just put 1 here. And our air is equal to 100 cm squared. And you have to take note of the units. It is in centimeters squared. And when computing for capacitance, all the measurement should be in metric systems. We have to convert the centimeters squared first. So 1 meter is equal to 100 centimeter, and since it is in square cm, so let's square this one. Yeah, so the centimeter square will be cancelled. Then our distance D is equal to 2 millimeter. That is 2 times 10 is negative 3, then meter. Okay, now we can solve for our capacitance. So constant 32 times 100 times 1 over 100 squared divided by 2 millimeter, and that is equal to 44.27 picofarad. Next example, so a capacitor whose plate is 20 cm by 3 cm and is separated by a 1 millimeter air gap is connected across a 12 volts battery. So determine the charge accumulated in each plate after a long time. So we have a formula Q is equal to CV, so that we can solve for the charge accumulated in each plate. Okay, so our capacitance, that is equal to EOER, A over D, and multiplied by voltage. Then we'll substitute our given. So this will be constant 32. Then ER is, it says here air gap, so that's equal to 1 permittivity. Our areas, we have 20 cm by 3 cm, so that is 20 cm. Okay, cm is times 10 raised to negative 2, so I'll just write it as 20 times 10 raised to negative 2. Okay, times 3 times 10 raised to negative 2 for the another cm. So that this is in meter. Then all over D, that is 1 times 10 raised to negative 3 meter, and multiplied by 12 volts. So our answer would be constant 32 multiplied by 20 raised to negative 2 times 3 raised to negative 2 divided by 1 millimeter, then times 12. So our answer is 637.50 pico, because this is times 10 raised to negative 12, and unit for charge is coulomb. So we have 637.5 pico. So we have your current voltage relationship for a capacitor. I is equal to C multiplied by dV dt, or the change in voltage with respect to time t. Now, if you will get the voltage, so we'll just manipulate this formula. So we'll have I dt is equal to C dV, then integrate both sides of the equation. We'll get V is equal to 1 over C integral of I dt from t0 to t plus b of t sub 0. Now this is the graphical representation of the current voltage relationship of a capacitor, where the y-axis is the current, our x-axis is the dV/dt, or the change in voltage with respect to time t, and our slope is the capacitance. Now, the instantaneous power delivered to the capacitor is the same as usual. That is equal to P is equal to VI is equal to CV dV dt. Then, solving for the energy stored in the capacitor. So, this is just a derivation of the formula. So, our final formula is omega, or W, is equal to 1/2 CV squared, or when it's in terms of charge and capacitance, so it's equal to Q squared over 2C. Now we have here properties of a capacitor. So when the voltage across a capacitor is not changing with time, the current through the capacitor is equal to 0. So that means the capacitor is an open circuit to DC. However, if a battery is connected across a capacitor, the capacitor charges. Okay? Then, the voltage in the capacitor must be continuous. The capacitor resists an abrupt change in the voltage across it. So, the voltage in the capacitor cannot change abruptly. So, as you can see here in the figure, so the voltage across a capacitor, so the first figure in letter A, it is allowed, or it can happen. So, this gradual increase and gradual decrease of voltage, but the second figure is not allowable because an abrupt change is not possible. Okay, so when dealing with capacitors and inductors, there is a mnemonic for for the first property. Capacitor is an open circuit to DC, so just have to remember disco. Okay, disco. So this means that D means DC. So in DC condition, our inductor, okay, so this one we will be discussed later. Our inductor is shorted, while our capacitor and is open. So just like what is written in our first property of capacitor. So this is a very important mnemonic for the property of capacitor and inductor. So at DC condition, inductor shorted, capacitor open. Next, the ideal capacitor does not dissipate energy. It takes power from the circuit when storing energy in its field and returns previously stored energy when delivering power to the circuit. A real non-ideal capacitor has a parallel model leakage resistance. So this is a circuit model of a non-ideal capacitor. So this is the capacitor and it has a leakage resistance. So this is a non-ideal capacitor. So we have here an example. Calculate the charge stored in a 3 picofarad capacitor with 30 volts across it. Find the energy stored in the capacitor. So this is just basic. So in letter A, let's just use Q is equal to CV. So our capacitance given is 3 picofarad. Then voltage is equal to 20 volts. So answer would be 60 picocoulomb. Then for letter B, the energy stored in the capacitor, that's W is equal to 1/2 CV squared. Okay, so 1/2. Then given capacitance is 3 picofarad. Our voltage is 20 volts, then squared. So our answer would be 600 picojoules. Okay, so remember that the unit for energy is joules. Then next example, the voltage across a 5 microfarad capacitor is V of t is equal to 10 cosine of 6000 t. Now we calculate the current through it. So we have here a formula of I of t is equal to C multiplied by dv dt, or the change in voltage with respect to time t. Okay, so let's just substitute the given. So our capacitance equal to 5 microfarad. Then the derivative of 10 cosine of 6,000 t with respect to time t. Okay, now let's just rewrite the capacitance. Then derivative of 10 cosine 6,000 t, that is 10 times 6,000 times negative sine of 6,000 t. Ayan. So our answer would be negative 0.3 sine of 6,000 t, and unit is ampere because this is current. So next example, determine the voltage across a 2 microfarad capacitor if the current through it is I of t is equal to 6 e raised to negative 3000 t milliampere, and assume that the initial capacitor voltage is 0. So we will use the formula V is equal to 1 over C integral of I dt from 0 to t plus the initial capacitor voltage, but it says here that the initial capacitor voltage is 0, so we will not consider this one. Okay, so let's substitute the given. So our capacitance is 2 microfarad. Integral of 6 e raised to negative 3000 t. Then we have here milliamps, unit milliamps, and dt from 0 to t. So let's just put the 6 milliampere separately. So let's write 6 times 10 raised to negative 3 over 2 microfarad. Then integral of e raised to negative 3000 t dt. Okay. Now integral of e raised to negative 3000 dt. So integral of an exponential function is just the same. So 6 times 10 raised to negative 3 over 2 microfarad. Then we will just consider the exponent, the negative 3000 t. So this will be 1 over negative 3000. Then multiplied by e, negative 3000 t, limits from 0 to t. Now, let's simplify 6 times 10 raised to negative 3 over 2 microfarad divided by negative 3000. That is equal to negative 1. Okay. So we have e raised to negative 3000 t, then limits from 0 to t. So negative 1 multiplied by this limit, so from 0 to t, so e raised to negative 3000 t minus e raised to 0, and e raised to 0 is equal to 1. Okay, so this will be negative 1, so times negative 1, so let's just write it first. 1 minus e raised to negative 3000 t, and unit is volts. Ayan. So this is our answer. Now we have here another example. Determine the current through a 200 microfarad capacitor whose voltage is shown in this graph. Okay, so we have here our horizontal axis is the time, and our vertical axis is the voltage. So we can write the mathematical representation of this graph first by plotting first the points. Okay, so let's say this is 0, 0. This is 150. This is 3, negative 50, and this one is 4, 0. Now, since this is straight lines and we have points, okay, so these are the points in the line, we can use the 2-point form to get the equation of these lines. No? So let's write this in here. Okay. Let's rewrite the points. And 150, 3, negative 50, and 4, 0. Okay. Now let's start with the point 0, 0, 150. So this line. Okay, so this line. Okay, so at 0, 0, and 150. So our 2-point form, that is y minus y sub 1 is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So as you can see, this is the formula for the slope. Then multiplied by x minus x sub 1. Now let's apply the 2 points. So y minus 0 is equal to 50 minus 0 over 1 minus 0 multiplied by x minus 0. So we have y equal to 50 times x minus 0, or y is equal to 50x. But our vertical axis is b of t, so this will be v of t equal to 50. Our horizontal axis is time, so this is 50t. And limit is from 0 to 1. So 0 to 1. Now, next points to consider is 150. Let's write 150 and 3, negative 50. So y minus y sub 1 is 50 equal to negative 50 minus 50 over 3 minus 1. So x minus 1. So this will be y minus 50 equal to negative 100 over 2 x minus 1. So this will be y minus 50 equal to negative 50x plus 50. So this will be y is equal to 100 minus 50x, or b of t is equal to 100 minus 50t. And our limit is from 1 to 3. Okay. Then next, our third point is from 3, negative 50, and 4, 0. So we have y minus negative 50, or y plus 50 equal to 0 plus 50 over 4 minus 3. Then x minus 3. So we have y plus 50 equal to 50 over 1 multiplied by x minus 3. So y plus 50 equal to 50x minus 150, or that is equal to y equal to negative 200 plus 50x, or v of t is equal to negative 200 plus 50t. Our limit is from 3 to 4. Okay. Now that we have the representation of the voltage, our formula for getting the current is equal to I of t is equal to C dV dt. Okay. So our capacitance is equal to 200 microfarad. Then given derivative, or let's uh, write the given voltage first. So our given voltage, we have 50t from 0 to 1, 100 minus 50t, 1 to 3, and 200 plus 50t, 3 to 4. Okay. So the derivative of this one, okay, derivative. So let's write this here. 200 microfarad multiplied by the derivative of 50t, that is 50. Derivative of 100 minus 50t is negative 50. Then derivative of negative 200 plus 50t is 50. Now let's just write the limits. Ayan. So our answer would be equal to 10 milliampere, negative 10 milliampere, and 10 milliampere. Of course, the same limits. Ayan. So we have here the answer. Now, we will try to graph. Ayan. So this will be the graph of our answer. So from 0 to 1, the value of current is 10 milliampere. From 1 to positive 3, current is equal to negative 10. And from 3 to 4, that is equal to positive 10 milliampere. Now let's apply the concept of capacitors in actual circuits to obtain the energy stored in each capacitor in the figure below under DC conditions. So as I've said earlier, under DC condition, our capacitors are open. Okay, so this 2 millifarad here and the 4 millifarad here will be open, and it will be look like this. Okay, so as you can see, it looks like we only have 2 kilo ohm in series with 4 kilo ohm, and 6 milliampere is in parallel with 3 kilo ohm. Now let's solve for the current first, this one. The current is flowing through the 2 kilo ohm and 4 kilo ohm resistor. So to solve for that, let's use current divider. So I is equal to 6 milliampere multiplied by the other resistor, that's 3 kilo ohm, over 3 kilo ohm plus 2 kilo ohm plus 4 kilo ohm. So this will be equal to 2 milliampere. Now, to solve for the V1 or the voltage of the capacitor here and here V2, so we can solve for the voltage drop in this resistor, the 2 kilo ohm, since they are parallel. So this is same voltage. So whatever we solve in the voltage drop of the 2 kilo ohm is just the same as the voltage across the capacitor. So solving for a V1, so let's just use Ohm's law. So IR, so 2 milliampere multiplied by 2 kilo ohms. So that is equal to 4 volts. For V2, so the same concept. So since they are parallel, so we have same voltage here. So our V2 is equal to 2 milliampere multiplied by 4 kilo ohms, so we have 8 volts. Now solving for the energy stored in each capacitor, we have omega 1 is equal to 1 half C1V1 squared. That is equal to 1 half. Our capacitor here is 2 millifarad. Then multiplied by 4 volts squared, that is equal to 16 millijoule. For omega 2, so same formula. So 1 half, our capacitor is 4 millifarad. Then our voltage is 8 volts. Squared, then we have 128 millijoules. Yan. So that is our answer. We have here series and parallel capacitors. So we have parallel capacitors. The equivalent capacitance is just the same as how we get the equivalent resistance in series. So we'll just get the summation of the individual capacitances. So C equivalence equal to C1 plus C2 plus C3 and so on and so forth. Then for series capacitors, so the equivalent capacitance is the reciprocal of the sum of the reciprocals of the individual capacitances. So, ayan, they are reverse of that resistance equivalent. Okay. So example, find the equivalent capacitance in between terminals A and B of the circuit in the figure below. So just like as how we solve equivalent resistances. So if we will find equivalent capacitance in between the terminal A and B, so we'll start with the farthest side. Okay, so in this case, we'll start with the leftmost part of the circuit. So 20 microfarad and 5 microfarad is in series. So since this is series, this will be 20 microfarad multiplied by 5 microfarad all over 20 microfarad plus 5 microfarad. And that is equal to 4, right? So this is equal to 4 microfarad. And 4 microfarad is in parallel with 6 and 20. So that would be just summation. Yan, summation. So 4 plus 6 is 10 plus 20. We have 30 microfarad. And 30 microfarad is in series with 60 microfarad. Therefore, our equivalent capacitance equal to 30 microfarad multiplied by 60 microfarad all over 30 microfarad plus 60 microfarad. And that is equal to 20 microfarad. So another example, find the voltage across each capacitor. So we will find the value of V1, V2, and V3 here. But before that, let us first find equivalent capacitance. So 40 millifarad and 20 millifarad is in parallel. So this is just summation. So 40 millifarad plus 20 millifarad. So this is equal to 60 millifarad. Then 60 millifarad is in series with 30 and 20. Therefore, our equivalent capacitance equal to 1 over 20 millifarad plus 1 over 30 millifarad plus 1 over 60 millifarad, then the reciprocal. And that is equal to 10 millifarad. Now, to find the voltage, we have to find first the charge, the total charge of this circuit. Find the total charge of the circuit. That's equal to Q is equal to C V. Let's write C equivalent here. So this is equal to 10 millifarad, then multiplied by our voltage source, that's equal to 30 volts. So this is equal to 0.3 coulomb. Now to find the V1, so V1, since the total charge is in series with 20 millifarad and 30 millifarad, so we can actually use the charge here to find the voltage drop or voltage for the capacitors. So using the same formula, so V1 is equal to Q over C1. So our Q is 0.3 coulomb divided by 20 millifarad. So that's equal to 15 volts. For our V2, so Q over C2, so 0.3 coulomb divided by 30 millifarad, and that is equal to 10 volts. Now, to find the value of V3, so we can just use KVL, okay? So, V3, that is equal to 30 volts minus V1 and V2, okay? So, that is equal to 30 volts minus 15 plus 10, or that's equal to 5 volts. Ayan. So, that is the values of V1, V2, and V3. Now let's proceed with inductors. So an inductor is a passive element designed to store energy in its magnetic field. Inductors find numerous applications in electronic and power system, and they are used in power supplies, transformers, radios, TVs, radars, and electric motors. So this is a basic representation of an inductor. So it's like a coil of conducting wire with a cross-sectional area A. This is the core material. Then the number of turns N, and the length L. So these are the factors or the parameters that we'll be considering when computing for the inductance. So we have here various types of inductors. So this one is the solenoidal wound inductor. This one is toroidal inductor, and this one is chip inductor. So the third one, it looks like a through-hole resistor at first glance, but it is much smaller size than the usual resistor. Then we have here the circuit symbols for inductors. For letter A, this is the error core. Then for letter B, this is iron core. And the third one is the variable iron core type of inductor. Now, if current is allowed to pass through an inductor, it is found that the voltage across the inductor is directly proportional to the time rate of change of the current. So using the passive sign convention, we have here the formula V is equal to L di dt, where L is the constant of proportionality called the inductance of the inductor. The unit of inductance is Henry, in honor of the American inventor Joseph Henry. And 1 Henry equals 1 volt second per ampere. Now, inductance is the property whereby an inductor exhibits an opposition to the change of current flowing through it measured in henries. So, capacitance a while ago, so it exhibits the opposition to the change of voltage. For inductance, it exhibits the opposition to the change of current. Okay, so the inductance of an inductor, as I've said a while ago, it depends on the physical dimension and construction. So our formula, L is equal to N squared mu A over L, where N is the number of turns. Okay, L is the length, A is the cross-sectional area, and mu is the permeability. So this mu is equal to mu O mu R again. Mu is, in our calculator, that's constant 33 if you are using 991 ES or 570 ES, and I think it is constant 15 if you are using 991 EX. Then mu R is permeability of relative permeability of a material. Then we can see from this equation that inductance can be increased by increasing the parameters in our numerator, like increasing the number of turns, the cross-sectional area, and choosing material with higher permeability as the core, or of course reducing the length of the coil. Now the current voltage relationship is equal to I is equal to 1 over L integral of V of t dt from t sub O to t plus I of t sub O. Then the power delivered to the inductor is equal to P is equal to VI or L di dt multiplied by I. So the energy stored is equal to omega is equal to 1/2 Li squared. So it looks the same with the energy stored in a capacitor. It's just that um, capacitance and the voltage is given. Now let's have an example. A solenoid 500 centimeter long and 10 cm in diameter is wound with 1,500 turns. Find the energy stored in the magnetic field when a current of 5 ampere flows. So formula for the energy, we have omega L is equal to 1/2 Li squared, but we don't have the value for inductance, so we have to solve for it first. That is mu O mu R, A n squared over the length. So our mu O is constant, 33, and our relative permeability for a solenoid is 1. Then our area, since the cross-sectional area of solenoid is circles, we will have the area of a circle, pi over 4d squared. Our d is 10 cm. 10 times 10 is negative 2 squared. Then our number of turns is 1,500. Then let us square that. Then our length is equal to 500 cm. Okay. So our inductance would be constant 33 times 1 pi over 4 multiplied by 10 raised to negative 2 squared 15 squared divided by 500 cm. And that is equal to 4.44 millihenry. Now to solve for energy, that is 1 half Li squared. So 1 half times 4.44 millihenry. Then our current is 5 ampere. So let us square that 1. So times 25 divided by 2. So our answer is 55.52 millijoules. Ayan. For example, a coil of 250 turns is wound on a closed iron ring whose cross-sectional area is 20 centimeters squared and a mean length of 100 centimeter. Determine the energy stored in a magnetic field if a current of 2 ampere is passed through it. Then assume the permeability of iron is 900. So just the same as what we did in the previous example. So omega L is equal to 1 half Li squared. And L is equal to mu O mu R A N squared over L. So this is constant 33. Then our permeability given is 900. Then our area is equal to 20 cm squared. And it needs to be converted into meter. Okay, ayan. Then number of turns is 250 squared. Our length given is 100 cm. Ayan. So, our inductance is equal to and 0.14 or 1 for 1 Henry. Then solving for the energy. So, that is 1 half Li squared or 1 half times 0.141 Henry times the current is 2 ampere squared. So we have 282.74 millijoules. Important properties of an inductor. First one, the voltage across an inductor is zero when the current is constant. Thus, an inductor acts like a short circuit to DC. So I've said a while ago, the mnemonics disco. So at DC condition, our inductor is shorted and our capacitor is open. Now, an important property of an inductor is its opposition to the change in current flowing through it. So the current through an inductor cannot change instantaneously. So like the ideal capacitor, the ideal inductor does not dissipate energy. The energy stored in it can be retrieved at a later time. It takes power from the circuit when storing energy and delivers power to the circuit when returning previously stored energy. So as you can see here in the figure, the first figure is allowable or it can happen. This gradual increase in the current, while the second figure is impossible or is not allowable because there is an abrupt change in the current. The practical or non-ideal inductor, so just like in the capacitor, so there is a winding resistance that appears in series with the inductance of the inductor. So the presence of this winding or winding resistance makes it both an energy storage device and an energy dissipation device. Since this winding resistance is usually very small, so it is ignored in most cases. So the non-ideal inductor also has a winding capacitance. So this is the winding capacitance due to the capacitive coupling between the conducting coils. CW is very small and can be ignored in most cases. So this is the circuit model for a practical inductor. Now, let's have some example. So the current through a 0.1 Henry inductor is I of t is equal to 10 t e raised to negative 5 t amperes. So find the voltage across the inductor and the energy stored in it. So our formula for the voltage is V of t is equal to L di dt. Okay, so our inductance given is 0.1 Henry. Then our current, so let's write the formula, 10 t e raised to negative 5t with respect to time t. So 0.1 Henry multiplied by the derivative of 10 t e raised to negative 5t. So that is 10 e raised to negative 5t plus 10 times e raised to negative 5t multiplied by negative 5. Okay, so distribute the this one has t, and so distribute the 0.1 Henry, so we'll have e raised to negative 5t, then minus 5 e raised to negative 5t. Or if we will factor the e raised to negative 5t, so this will be 1 minus 5t. Unit is volts. Ayan. Then, to solve for the energy, so that is WL is equal to 1/2 Li squared. So 1/2 multiplied by the inductance 0.1 Henry. Then current is 10t e raised to negative 5t, then squared. So our answer would be 5t squared e raised to negative 10t. Okay, because this will be 10 squared, so 100 times 0.1 divided by 2, that will be 5. Then t, so squared lang. Then e raised to negative 5t squared is equal to e raised to negative 10t. The unit is joules. Another example, find the current through a 5 Henry inductor if the voltage across it is E of t is equal to 30 t squared if the time is greater than 0, and 0 if t is greater than 0. So find the energy stored at t is equal to 5 seconds. Assume I of v is 0. So our formula, I is equal to 1 over L integral of v dt, okay, plus the initial value of current. But since assumption is I of v is equal to 0, this is equal to 0. So we will not consider that one. Our limits is from 0 to t. Now let's substitute the given 1 over 5 Henry, then integral of 30 t squared dt from 0 to t. So we have 1/5 multiplied by 30 t cube over 3, or this will be 30 divided by 15, or 2t cube ampere. Okay, so that is the current. Now to solve for the energy, so that is integral of p dt. We can use this formula, but we have to solve first for the power, which is equal to VI. So our voltage is 30 t squared. Our current is 2t cube. So we have 60 t raised to 5. Then let us substitute this one here. So our power is 60 t raised to 5 dt. Then Energy stored at t is equal to 5 seconds. So therefore, our limit is from 0 to 5. Okay. So this will be 60 t raised to 6 over 6 from 0 to 5 or equal to 156.25 kilojoules. Ayan. Then another example, consider the circuit below. So under DC conditions, find the current and the energy stored in the capacitor and inductor. So in DC condition, our capacitor is open, then our inductor is shorted. So just like this one. So we will have a circuit with 1 ohm in series with 5 ohm. So to find this current, so just Ohm's law, so I is equal to 12 volts divided by 1 plus 5, or that is equal to 2 ampere. Now, if we will look for the value of BC here, so as you can see, this is in parallel with the 5 ohm, and parallel means same voltage. So therefore, our BC is equal to the current, so 2 ampere multiplied by the 5 ohm, and that is equal to 10 volts. Okay, so finding the energy stored in the capacitor. So in the capacitor, let's say that is WC or omega C, 1 half CV squared. 1 half capacitance is 1 farad. Then our voltage is 10 volts. So squared natin. Then we'll have 50 joules. Now for omega L, that is 1 half Li squared. That is equal to 1 half. Our inductance is 2 Henry. Current is 2 ampere. So equal to 4 joules. We have series and parallel inductors. So dealing with series and parallel inductors, just like dealing with series and parallel resistances. So if we have series inductors, to find equivalent inductance, we just only have to get the sum of the individual inductances. Then for parallel, so reciprocal of the sum of the reciprocals of the individual inductances. So example, find the equivalent inductance of the circuit below. So we have here a series 20 Henry and 12 Henry and 10 Henry. So this will be 20 Henry plus 12 Henry plus 10 Henry. And this is 20, 32, 42 Henry. Okay, and 42 Henry is in parallel with 7 Henry. So that will be 7 Henry multiplied by 42 Henry over 7 Henry plus 42 Henry, and that is equal to 6 Henry. So our L equivalent is summation of 4 Henry plus 6 Henry plus 8 Henry, and that is equal to 18 Henry. Yeah, so we have here important characteristics of the basic elements summarized in this table. So if we have a VI relationship, for the resistor, we have V is equal to IR. For the capacitor, that's V is equal to 1 over C, integral of I dt plus V of T sub O, limits from T sub O to T. Then inductor is V is equal to L di dt. For IV, so just manipulation of formula. So I is V over R, C dV dt. Then 1 over L integral of V dt plus I of T sub O. For power, so just the same, P is equal to I squared R, V squared over R. Then energy for a capacitor is 1 half CV squared. Energy for inductor is 1 half Li squared. Then if we have series resistor, so just summation, so like the series inductor. And the opposite of that is the capacitor, so it looks like the parallel combination of resistor. So C1, C2 over C1 plus C2. And yan, parallel. So R equivalent, R1, R2 over R1 plus R2. So just the same again with the inductor. Whereas with the capacitor, just the C summation. And again, for DC condition, resistors is the same, capacitor open circuit, and inductor is short circuit. Now we have here the applications of capacitors and inductors. So it possesses three special properties that make them very useful in electric circuits. So the capacity to store energy make them useful as temporary voltage or current sources. So they can be used for generating a large amount of current or voltage for a short period of time. Then capacitors oppose any abrupt change in voltage, while inductors oppose any abrupt change in current. So this property makes inductors useful for spark or RX suppression and for converting pulsating DC voltage into relatively smooth DC voltage. And capacitors and inductors are frequency sensitive. So it makes them useful for frequency discrimination. So the first two example here of the application are put into DC, whereas the third one is for AC circuit. Okay. We also have integrator, an op-amp circuit whose output is proportional to the integral of the input signal. So this is an example of an integrator. Here, replacing the feedback resistor in the inverting amplifier produces integrator. And a differentiator is an op-amp circuit whose output is proportional to the rate of change of the input signal. So this is an example of an op-amp differentiator. So as you can see, we have here capacitor and resistor here. For the integrator, we have resistor here and capacitor here. So that's the symbol for them. Then last one, we have analog computers that can be programmed to solve mathematical models of mechanical or electrical systems. So these models are usually expressed in terms of differential equations. And to solve simple differential equations using the analog computer requires cascading three types of op-amp circuits: the integrator, the summing amplifier, and the inverting or non-inverting amplifier for negative or positive scaling. So that's the end of our discussion. So if you have some questions, you can just take down in the comment section, and don't forget to like and subscribe our video. So yeah, thank you for listening.